Login accepted.
Hello, everyone. My name is Michał El Fartas. I'm DevOps Tech Lead at Egnyte Poland. And my topic today is autoscaling versus high availability in Kubernetes. As you may have noticed, it's not autoscaling and high availability, it's autoscaling versus high availability. I've been working with Kubernetes for the last 5 years, so I'm not going to bore you with some tutorials and simple demos that always work. I'm going to show you like real-life problems, real-life issues that we had deploying Kubernetes at scale. I mean, Kubernetes is suffering from what I call a tutorial-driven development. Basically, you see Kubernetes at a conference, you see that's a great technology. You run a tutorial, you see it actually works. You may even run a POC at your company, migrate some non-critical service, it works as well. But then you decide to migrate all other critical services, and suddenly there are problems, and you don't know how to tackle them. So this is what we're going to be talking about today. Our agenda is first, we're going to start with some basics, talk about cluster autoscaling, how that works, how it can actually impact the underlying infrastructure, how it can impact your networking, the availability of your components, where you need to know some of like classical operational stuff, even if you're a developer developing charts for Kubernetes. And then we're going to move to pods autoscaling, how to observe the autoscaling behavior, how to tune it at the scale, and what are the benefits, what are the pitfalls of the autoscaling. So before we start, can I get a show of hands? Who is currently using Kubernetes? Cool. So we can probably skip some basic stuff. Who is actually using Kubernetes in production? Good. That improved over the years, so that's a good thing. And who is managing Kubernetes cluster? Okay, so I guess most of you are developers, you develop charts, you deploy stuff on Kubernetes, you don't necessarily manage the cluster. That is fine. That's actually great because you can probably pick a lot of insights that you previously didn't know about how to deploy the charts, how to configure them. So before we jump into those pitfalls, let's start with basics. So how the autoscaling works. We need to cover that because Kubernetes often abstracts from the infrastructure. So you don't really realize what's actually going on underneath. So those are the basics. I guess we can skip that mostly. So we have pods. Pods are containers. Pods are deployed on the nodes. Nodes are server in a cluster. Deployment specifies what is the specification of a pod, how many replicas it has. And the key parts we're going to focus on are cluster autoscaler that scales up a cluster, adds new nodes, or downscales it, and scheduler that assigns pods to the nodes. Those are key components to look at autoscaling in the aspect of the high availability. So how scheduler works? Pretty simply, you have resources. Usually it's CPU and memory. Sometimes you have also GPU. And scheduler role is assign pods to nodes that have the resources that the pod needs. And also to respect the constraints such as node selector, taints, affinity, anti-affinity, basically your policy for assigning the pods to the node. Nodes define capacity. Usually it's a bit less than the node specification. You have some allocatable amount of resources. Usually it's CPU, memory, specified by your cloud provider or your operations team. And the pod defines the request and limits, so basically how much a single pod needs resources. Node hosts many pods, and usually you can, with kubectl, can see how much, what is the usage of the node. So let's see scheduler in action. This is like a simplified cluster, we have 2 nodes. Let's say each node can host 2 pods. Let's simplify the resources just for the sake of this exercise. So the most basic case, we create deployment Z on an existing cluster. We want 1 replica of a pod Z. So we make an apply, scheduler take a look at the cluster, see node 2 has capacity, allocates pod Z1 to node, it's done. Simplest case. Now we want to scale deployment Z to 2 replicas. We decide, okay, we want some high availability, like 2 replicas. So let's start with somewhere. So scheduler noticed that we have insufficient resources. So then cluster autoscaler appears. What it does, it provisions a new node. Node is created, pod is scheduled. Everything works great. This is why we use Kubernetes for this stuff. Now we decide we want to remove deployment. Why? Why not? So we remove it. The scheduler terminates the pods. Pods are removed. And this is the current state of our cluster. So as you can see, we have 3 nodes in the cluster, 3 pods, and basically we're using half of the cluster capacity. So what happens next? Scheduler and cluster autoscaler notice cluster is underutilized. And what happens is that pod Z2 is evicted. Basically, scheduler and autoscaler decide which node to free up to reduce the cluster size. So we still need 2 replicas of pod Z. So scheduler creates a new pod on node 2, and the autoscaler removes node 3, and we get downscaling. So that's the basic. That's basic stuff, how upscaling then downscaling works in Kubernetes. Now, where in that scenario you can start having problems with high availability. So first, let's say, what's the definition of high availability on the practical front? So basically, it's a replication and fault tolerance. We've seen replication. You could specify multiple replicas. It's simple in Kubernetes. Now let's focus on fault tolerance. Most basic case, node failure tolerance. So we had this scenario where previously we had the downscaling. So what happens now is the server dies. Servers die. They do. And basically, you have to be prepared for that. It's most common type of failure. And what happens in this scenario, even though you had 2 replicas of the deployment Z, it crashes. It is unavailable. So how to prevent that? Very simply, you specify something called pod anti-affinity. So basically, you tell the pods in the deployment, especially you tell scheduler, to spread out the pods across different hosts. So we define stuff like which labels should be matching and what's the key you want to spread out. So in this case, it's a host name. But you can also specify other keys like zone or region if you have a bigger cluster. So you can spread out your application between multiple zones in your cloud provider. So what happens with this policy applied? Well, if we take a step back, so when the cluster autoscaler was deleting the node, the scheduler sees that, okay, node 2 already has the pod from the deployment Z, so let's schedule it to node 1 instead. And yeah, one thing, you can specify different types of this behavior. So you can have anti-affinity to spread out stuff, affinity to collocate stuff, and you can also specify multiple conditions. As you can see, you have a weight. And in this scenario, this is a preferred during scheduling. So basically, it's a soft requirement, not a hard requirement. You can also set required, and then scheduler is forced to respect that requirement. So next case is something called eviction tolerance. So now we have the anti-affinity applied. Basically, usually most of the people have that already. It's in most tutorials. You can find it easily. But what happens now? You get a bit bigger cluster, 4 nodes. And we have the same situation where cluster is underutilized, right? We use probably half the capacity. We have the deployment Z in 2 replicas. We have anti-affinity is deployed to different nodes. And what happens now? Scheduler decides to evict both pods Z1 and Z2. And what you get is another interruption of service. You can think, okay, why? Why did it happen? I mean, you had specified two replicas, you had specified anti-affinity. Well, because there is another object of that. It's called pod disruption budget. And what I've seen is this is the most commonly omitted thing in Kubernetes deployments. Basically, with pod disruption budget is you define a policy for scheduler to respect how available should your application be for the, let's call them, maintenance operations. So that includes cluster upscaling, downscaling, as well as cluster upgrades. This is pretty important if you have a GKE, for example, cluster with auto upgrades enabled. Because with that, scheduler can do something you could think of as a rolling eviction. So in this previous scenario, it would first see, okay, let's evict one pod from deployment Z, and then the other, or possibly choose a different node for that. So that's why it's, if you're serving an API, if it's something you have to have available all the time, it's important to specify pod disruption budget. You can specify it on different approaches. You can specify minimum availability, then you have to have, or max unavailable. Just be careful because you can also specify a policy where you do not allow evictions, and in some cases it can actually break the upgrade. So basically, at some point, the scheduler will fail the cluster upgrade because it cannot respect the policy if, let's say, you have you don't allow any unavailable pods, and let's say you have one pod with a database or something like that. So be careful about that. And now we get to another part, the stuff that's not often talked about, because the previous stuff you can probably find on the tutorials and good practices pages, etc. But the thing that's often omitted when talking about Kubernetes is underlined networking. Why? Because it's complicated. And people try to look at Kubernetes networking as it works. I install a service or an ingress, and it works. And I don't have to worry about the magic that goes underneath. Let's talk a bit about this magic. So we're going to focus here on load balancing and traffic policy. So what we have here is the most common case of a load balancer. And I'm talking about external load balancer, not internal in the cluster. You create a service type load balancer. Load balancer is created. You get an IP. You can make requests. It gets routed. Works perfectly. You're happy. You didn't have to call your ops guys. Everything works, right? How it works is load balancer will route the traffic to all the nodes in the cluster, even the ones that don't have the pods. And then when the request reaches the node, then it reaches kubeproxy, which routes it to a node that has the pod. So it may seem, okay, it's a bit convoluted, you have additional hop, but that's the way it's implemented by default, because it's the simplest way to balance this stuff out. So let's look at potential request. You have a user, it gets routed to node 1, even though it doesn't have any of a pod Z from the service Z. And then kubeproxy proxies it to pod Z1 on node 2. Now, if it's a short call, simple request, not a problem. But let's say you're uploading a 2 gigabytes a file. A large upload, it's a long request, it takes time. So what can happen now is a wild autoscaler appears. And now, even though you have pod disruption budget, anti-affinity, multiple replicas specified on the pod Z, and it's fully operational, autoscaler decides to delete node 1, and your connection gets interrupted. That's one of the things you have to think about. And actually, an interesting cases can appear even without the autoscaler Because if you have a cluster with mixed workloads, and you have, for example, a pod that does very intensive processing on the node, and, for example, consumes all of CPU, we've seen cases where it can actually impact network traffic, and suddenly your requests get slower because they get routed through a node that's overutilized. So what can we do in this scenario? Well, there is something called external traffic policy. Basically, you can have it on a default mode, which is cluster, or you can specify local traffic policy. What it does, it tells the load balancer to route traffic only to the nodes that have that pod, and then on that node, the traffic is routed directly to the pod. So you avoid additional network hop, it doesn't hide client IP, and it gets directly routed. So you think, okay, maybe that's the solution. So what happens now is every node in a cluster exposes additional health check on a port. Load balancer checks the health check, and the health check tells the load balancer, does this node have this pod? Right? So in this case, load balancer can easily see that, okay, node 2 and 3 have pod Z, and the kube proxy is also aware of that traffic policy and routes only to the pod within that cluster. Cool. So, job well done. It works. Well, until you get to your first deployment. Why? Let's look at this scenario in the aspect of a big wider cluster. So we have node 1 and 2 as previously, but now also we have node 3 and 4 that, let's say, have additional capacity. The health check is green for those two nodes. Load balancer routes the traffic. We have pod disruption budget. We have anti-affinity. So what happens now when we update deployment Z? We want to update the image, change the configuration, deploy a new version of application. So what happens now is version 2 of deployment Z gets scheduled on node 3 and 4. Why? Because you have specified anti-affinity, right? So it's gonna want to schedule on the different nodes. So deployment waits for pods to get ready, right? Let's say we have a good application running on Alpine. It starts quickly, health check passes, it's green. So it passes, deployment removes old pods, health check on the nodes changes. It's all good. But as you can see, load balancer is still routing traffic to node 1 and node 2. Why that happens? Well, there is a refresh lag on load balancer. If you think about it, it's still a classic load balancer, which you'd usually had to set up on normal VMs, and it has a health check and a refresh lag on a health check, usually like 5 seconds, something like that. So in this scenario, even though your service is internally available, it's running, it's up and running, you will get probably a few seconds disruption with it. So what can we do about that? Like with first scenario, we had the problem of interrupted connections. Here we have interrupted connections on deployment. What's up with that? Well, you remember this anti-affinity? Well, what we can do now is say hi to its bigger brother, do something like that. So this is somewhat of a hack, but it shows you nicely what can you do with Kubernetes scheduling, right? What kind of exercises you can do. So in here, we still specify the anti-affinity for the host name, for the pods with the same name. In our case, it's L1 proxy. But we specify anti-affinity. We narrow it down to the same pods, pods of the same deployment, but in the same version. This is a custom label that we decided to add. So pods of the deployment in the same version are going to be spread out as much as possible. But at the same time, we specify affinity, where we tell the pods of the same deployment, but in a different version, to try to collocate on the same nodes where the previous version was deployed. So what happens now is that if we deploy a new version, a new version is going to try to be deployed on the same nodes as the previous. So in this case, the health check doesn't need to change because the same nodes are still serving the same pods, the same service. Obviously, this is somewhat of a hack. It works well. We tried that. But it has certain edge cases. So let's sum it up. Which traffic policy should I use? I want my service to be up all the time, but as you can see, both have some drawbacks. So in my opinion, if you're starting with your new cluster, if you don't have any issues, use the default. It's a default for a reason. It works usually good enough. It's especially good when your front serving container is auto-scaled. Then definitely you should use this policy. And it's good when most of the nodes in a cluster are serving services, right? If you don't have this big, heavy workloads in the background. And in this scenario, avoid long-running connections and implement retries on the client side. Pretty logical. On the other hand, use policy local when cluster is aggressively auto-scaled. When number of nodes in a cluster constantly change, then local policy is better because you don't confuse the load balancer. Load balancer can target only those pods that you need. And also if your service serving stuff is only a small part of a cluster, right? And it's best used, in my opinion, with stuff like ingress controllers and API serving stuff. But there is also a third option. Unfortunately, right now, I only seen it implemented in GCP for GKE. It's called container native load balancing. In my opinion, that's probably going to be a way forward in a few upcoming years in other providers as well. What GCP does, it uses a native IP networking support. Basically, it has something called alias IP that makes pods IP globally reachable in the network. So you don't have to be in a cluster. You can simply be in a network, call pod via its IP, and you will get and you'll reach it immediately. And the benefit of that is that you don't have to think about nodes in the load balancer in this scenario. You can basically load balance directly to the pods from the load balancer. And how it works is you have a controller in the cluster that updates list of pods, the IPs of the pods in the load balancer. And you also get non-disruptive deployment. How? Well, in this scenario, as I said, load balancer now is able to speak directly to pods you want. So you avoid this additional hop. You don't even go through kubeproxy. You go directly to the pod. And you have the controller that controls the behavior. So now when we decide to deploy another pod on the deployment Z, the controller updates list of IPs on the load balancer. But to prevent the issue that we have with health check lag, etc., this time the load balancer and control impacts the behavior of deployment because now the pod is considered ready by the deployment only after the load balancer IP list is updated. This is something called readiness gate. So basically, you can have health check on a pod, say, OK, I'm good, but the deployment will not consider those pod ready until it gets additionally notified by the load balancer that, OK, we're good, running fine. Then only then it will delete all the replicas from the previous version. So that concludes basically the first part, the cluster autoscaling. Now we can move to the more interesting part, the pods autoscaling and basically scaling your application, right? The issues mentioned previously, it's something to be aware of. It's not something that occurs every time, but at some certain scale, it's going to happen to you. So something to remember and to safeguard yourself against. But now let's talk about pods autoscaling. And to talk about that, let's first get some background on what we do, because it's meaningless to talk about autoscaling, about certain cases without some business background, why we do the autoscaling. So a few words about the project that I've been working on. And it's our secure and govern platform at Egnyte. And basically, the main part of our processing that we do is files processing. So we download files, we do then text extraction, OCR, pattern matching, detecting sensitive content, and running it against multiple machine learning models. And what can you probably guess about this stuff? It's very heavy on the resources side. So it requires a lot of CPU, a lot of memory. And you can see that this is currently the capacity of our largest cluster. Right now, it's over 20,000 CPU cores, 50 terabytes of RAM, and over 3,000 application pods running. And what it means is it's costly. So that's our main reason for using autoscaling. Save money when you don't need those resources because every VM is expensive. Additionally, those files that I talked about, we get that from the sources that customer register, stuff like Egnyte domains, OneDrive accounts, G Drive, Box, Dropbox sources, Windows servers, etc. So those are live data sources where people work on, people add new files, modify files. And actually, if you look at this chart, this is our cluster size from last 7 days. You can actually see here the spikes in number where you have US business hours. So basically, this is when people, our customers, are working, and you have to upscale. You literally see the business hour on the cluster size. By the way, this is weekend, so obviously it scales down. So basically, this is the behavior that we want with autoscaling. Adjust to current traffic, to current workload. The third reason that we need autoscaling is also that we can get customer deals where customer comes with hundreds of terabytes of data. And when sales team does a good job, you can get multiple customers like that immediately. And there is no argument. You cannot say, well, we don't have capacity to do that. You have to scale up to deliver the same kind of performance for every client because that's what we're expecting. That's what we're paying for. So yeah, this is currently our infrastructure. And let's talk about this autoscaling now. So how do you realize autoscaling Kubernetes? Obviously, horizontal pod autoscaler. It's been for a while. Also, it's still actively developed, still beta for many years, and it's being constantly modified by Kubernetes. So keep an eye for that. Depending on which version you're using, you can have different features. But the basic is you specify minimum and maximum amount of replicas. You specify your target for the deployment or stateful set, and you specify metrics that you want to be scaled based on. The autoscaler periodically checks those metrics, calculates number of replicas, and changes your deployment. The amount of replicas increases, decreases. Pretty basic stuff. What can it use for metricas? Well, the basic stuff is resources. So this one was the earliest one deployed on the Kubernetes. So you could have CPU utilization, and it would calculate the CPU utilization across all pods and try to match your target value. So you could specify, I want 60% CPU utilization across the pods, and autoscaler would work to respect that. So the resource one are natively supported by Kubernetes, so you have CPU and memory. Then you could specify a pod metric. So basically, you expose metric from the pod, and then autoscaler calculates that across your pods, so stuff like requests per second on a single pod, active connections, stuff like that. Or you could use an external metric, stuff like load balancer requests per second, or maybe your queue backlog, stuff like that. So how do we use it? And what we have is like a queue-based, pipeline-based processing. So as I mentioned, you have like a queue for files to download, files to extract content, to process the content, to run some predictions, etc., etc. We use Google PubSub for that, but basically it could be any queue. And we have varying number of requests over time. So as I said, in the business hours, you have more requests. When it's night or weekend, it goes down. And also processing duration for each request is different because you could have simple files, empty files, or you could have a huge PDFs or Excel files that take a long time to process. So it's difficult to predict for each message in the pipeline how long the processing will take. And finally, something to consider, it's analytical processing. It doesn't have to be real time. So that's important information because knowing that, you can optimize for cost instead of optimizing for real-time performance, right? So in this scenario with heavy processing, we can focus on the most efficient processing. And basically we have the, for example, this file that's downloaded, queue, and we use metrics, number of undelivered messages, so basically a backlog size, most basic stuff on the queues. And also we use all this unacknowledged message, basically a backlog age. We use that as a compensation because, as I said, the processing duration could vary from request to request. So you need to be able to adjust to that, not simply blindly follow the size of the backlog. So what's the issue? I've showed you configuration, I've showed you replicas. Does it work? Yes, it works. But at certain scale, we started seeing some issues. Let's take a look at this simulation. So basically what we have here is backlog size, backlog age, and the calculated number of replicas based on those two things. So this green area is basically everything works as intended. You have a bit more messages, a bit less. Number of replica adjusts itself. It's all fine. But let's say now you have to stop the processing. Either there is a maintenance, or maybe your deployment process requires the pipeline to be stopped, or there is a bug and for some reason you stop processing or there is an incident. So what happens now? Replicas go down to 0, backlog size stays the same, but backlog age starts rising. The messages are getting older and older as they stay in the backlog. So what happens now when we resume processing? Now, because of the high backlog age, number of replicas spikes up. And what that means is we provision much more replicas than we need to process our input throughput, right? So what happens with the backlog size? It suddenly drops. But just because it drops, backlog age doesn't drop because it's still the age of all those messages that were waiting during that maintenance. Until we finish processing all those messages that are waiting, the backlog age will not drop. So we still scale up. And what happens now, at some point, we process all the messages, backlog size goes to 0, backlog age suddenly goes to 0, and our replicas go straight down to minimum, to 1. So what happens now? Now we have too few replicas to process the input to the queue. So what happens then? Well, the backlog size suddenly rises, age rises sequentially, and what we end up is this type of fluctuation. Basically, until it evens out over time, you will get this kind of fluctuation when you suddenly upscale, process too fast, downscale, process too little, upscale, process too fast. And when you have a pipeline where one stage of a processing puts a results to another stage of processing, to another stage of processing, you suddenly get this fluctuation all around. And basically what it means, you provision new VMs, deprovision them, create pods, delete pods, etc. Why is that an issue? Let's talk about that in a second. And to show you that it's not simply an Excel simulation, it's not a theory simply, This is an actual number of replicas that we had on two of our services in the pipeline. And as you can see, the behavior was like that. You get around 50 pods, and then suddenly it jumps to 400, drops down, jumps up, drops down, jumps up. And each of those is provisioning new VMs, deprovisioning them, etc. So what are the consequences of such a behavior? Well, first of all, startup and teardown down. If your horizontal autoscaler decides to scale up, then first, the cluster autoscaler has to create new VM. The new VM has to be provisioned. It has to start up, register in the cluster. New images have to be downloaded. Application has to be started. And all that time is the time that you pay for, but you don't use for processing. Basically, it's a complete waste of money. You waste that time. And the same goes with teardown. It's unless you have aggressive policy on the cluster autoscaler, you will have the behavior where horizontal pod autoscaler downscales the pod, and then it will take some time until cluster autoscaler kicks in and downscales the cluster. So basically, you have VMs that are provisioned, you pay for them, nothing runs on them. Furthermore, there is application warm-up. Unless your app is completely stateless, if so, good job. Then you have some connections to database, some connection to cache. You download some context, some settings, stuff like that. Constantly provisioning, deprovisioning the applications put also stress on those kind of components. Basically, if your database suddenly gets 400 additional connections, even if it's just for simple stuff, it still has to process all those connections, get them. It's usually some simple requests, but still it can put additional pressure that you don't need because you don't benefit from that. Furthermore, downscaling is interrupting current processing. So basically, if your application downscales, if you're processing a message in a queue, you probably have to acknowledge it at the end. So it will get retransmitted, but the effort that you spend on processing that, if you have something that takes, let's say, a minute to process, that's the processing that goes to the trash. It's get thrown away because the interruption is killing everything. And final thing that is actually often omitted is scattered metrics. So let's say you have in your application performance metrics. You measure the usage of the JVM, the metrics on the processing, stuff like that. Well, if your autoscaler creates a pod runs 4 minutes, and then it's getting killed, the metrics from that period is probably not going to be useful, right? What you normally expect when you design those metrics is to have metrics over a period of time. Even if you can collect some metrics, usually if you use like a Grafana or something like that, the charts will be scattered, the data points will be unclear. Basically, even your metrics are going to suffer from that. So what can we do about it? In Kubernetes 1.18, a new feature appeared, which is called the scaling behavior. What does it do? By the way, it's only available in Autoscaler V2 Beta 2. That's the recommended version. Don't use any other version. And what it does, it introduces a behavior policy for the autoscaler. You can specify this behavior for scaling down and scaling up. And you can specify here a policy. So what we have here is for scaling down, we specify that for a period of 5 minutes, the autoscaler cannot scale down more than 25%. Even if metrics shows it can go down to 0, we specify this from 100 pods, it can only go down to 75% and has to wait 5 minutes until it reevaluates the metric and applies our policy. And on scale up, we have 2 policies this time. One is 50% and also 20 pods. And in here we have selected policy max. So what does it mean? Well, if you had 10 pods, you're not going to increase by 5, you're going to increase by 20. So you're going to have 30 pods. From 30, you're going to increase to 50. But from 50, you're going to increase to 75. So you can specify the behavior depending on the scale. So you can have a quick startup for smaller number of pods, but then bigger increments on the when the cluster gets bigger, when we're talking about some serious workloads. And what does it give us? So the benefits of that is more stable and more predictable scaling behavior. It's not as responsive as previously, but as you've seen, this being too responsive can actually cause some issues, some instability. So with this, you can get more even out scaling, and you can see how it actually evens out. Furthermore, you get increased overall throughput and efficiency because you're not spending so much time provisioning, deprovisioning. You're not wasting that time. And you get lesser pod variation. So the pods that existed will probably continue living for a longer period of time. And to show you that it actually works, this is the chart showing our number of replicas before applying the behavior and after. So as you can see, sure, we still have those spikes, but the large amount of pods continue on living. And you have much less variation in the pods, much more stable cluster behavior, and show an actual effect on the application. This is the PubSub acknowledgement metric. So basically, how much do we process in that time window? And as you can see, since we're no longer spending so much time on simply provisioning stuff, waiting for them to start up, the throughput increased and became much more stable over time. And I'm not talking about this only as something that can be showed in a metric and calculated only here. We actually have seen a significant drop in cost on our GCP billing after applying this policy. We're maintaining the same kind of amount of requests, but suddenly we pay a lot more or less. So on a final note, I want to review some final tips and good practices for the application for the autoscaling. So for massively autoscaled apps, as you've seen, stuff scaled to like 2,000 replicas, stuff like that. First of all, make it stateless. As much as you can, make the processing stateless. Put as much stuff into the messages. The more stateless it is, the better time you're going to have. Next, obviously, quick startup, lightweight containers. In the scenarios where we have to provision new VMs constantly, then lightweight containers means that the image is going to be pulled down faster, because if you provision new VM, obviously you have to pull the image. You don't have that already on your VM. And quick startup means you waste less time on idly warming up, and you can start processing as fast as possible. And finally, obviously, fault tolerance. It's pretty much became a standard now. But what I would propose is add some metrics to the fault tolerance. Stuff like, for example, how many times was message retransmitted? This is the metric that I found pretty valuable when judging this kind of like the scattered behavior. So basically, we had the metric which told us when acknowledging a message, how many times did it get to our application? On which attempt did we actually finally process it? So basically, that tells you if you have a lot of interrupted processing in the meantime. As for the infrastructure, if you fulfill all those kind of conditions and have autoscaling and have retransmission, my advice is you can leverage very cheap VMs. For example, in GCP, we used preemptible VMs, which are VMs from Google, that Google tells you after provisioning them, they will be killed within 24 hours. You don't know when, but at some point, they will simply shut down the VM, and you can get a new one, but you never know when it's interrupted. And the benefit of those are they're 80% cheaper than normal VMs. It was very beneficial for our processing, where we require a lot of CPU or a lot of memory, and Kubernetes basically, it makes it very easy, because when VM dies, new one is provisioned. And finally, be mindful of supporting components. Stuff that, bottlenecks that you're probably normally not aware of. When you're thinking about scaling application, think about bottlenecks like database, cache, maybe some rabbit, stuff like that, queues, stuff like that. What people often don't think about is monitoring, logging can become your bottleneck. I cannot remember how many times we've killed our logging pipeline by scaling up, and let's say in a new version, developer added additional logger. Suddenly, we get flooded with messages. The thing gets stuck at scale. Stuff like that can be pretty annoying. And actually, one time we managed to even kill our image registry by scaling up too much, making too many requests to download. Suddenly, the images were no longer being downloaded with scale. And finally, Kubernetes DNS and API, especially kubedns. So be watchful for that. It has a tendency to fail. Thankfully, recently, there is a trend to replace that with other alternatives. But yeah, kubedns and API can also, at some scale, turn to be problematic. And that's it from my side. You can download presentation using this link, and also we're hiring, so looking for new people. As you see, we have a pretty big scale and it's constantly increasing. We're in need to get new people, so you can use this QR code or ping me on LinkedIn or talk with me after the talk. I can share with you details. What do we do? How do we deal with our scale problems? So, do you have any questions? If not, feel free to talk to me after the presentation. Thank you very much.